All right, let's keep going here. Just trying to wrap up this this outlook discussion. So I just want to say a couple of quick things about autoignition, because that's also such an important kind of driver for if you want to think about where kind of combustion R&D problems flow into meets the real world. Autoignition is just such an interesting challenge. But you know, if you're going to run premixed, premature ignition's a significant concern. You know, as you can see from this plot that I showed you earlier, you know, as you increase, if you want to drive down NOx, you want higher mixing. Better mixing means longer residence time, which makes systems more. So you're always trying to trade off autoignition and NOx, particularly in higher pressure ratio machines. And you know, and you've probably seen plots like this, but this is an explosion diagram where, you know, this is pressure, this is temperature, and if you're in the top right, the mixture, if you give it enough time, is going to autoignite. If you're in the bottom left, it won't. And if you do happen to sit in the top right, the next important question is, well, how long does it take for a mixture to autoignite if you put it under those conditions? And you want to make sure your residence time is less than that. But what you can see, for example, the main point here is that, you know, you got to be at a higher pressure and a higher temperature for methane than, say, propane, and the difference is pretty large. And so if you start thinking about, and then this plot just further expands on this. This is a whole bunch of fuels, and this is sort of a ignition temperature, and I think this is at 1 atmosphere. I can't remember. This is autoignition temperatures as a function of average carbon chain length. So the very top left is CH4, and you know, C2H6, C3H8. You know, you see that autoignition temperature dropping, and then you start looking at, you know, like normal octane or normal decane or normal dodecane. You know, temperatures are dropping, and so it's just getting easier and easier to ignite. And this is why for liquid-fueled systems, well, and obviously you're becoming a liquid as you move to the right as well. And so liquid-fueled systems, autoignition is such a hard problem because what you'd really like to do is do what we call lean, pre-mixed, pre-vaporize. You'd like to take your liquid fuel, you'd like to vaporize it, and then you'd like to pre-mix it. That takes time. It takes more time than a gas because you got to pre-vaporize it, but you actually have less time because the fuel auto-ignites so easily. And this is why, if you look out there today, it's, you know, people are trying to kind of get in that direction, like GE, some of General Electric's aerospace, some of their engines are trying to push in this direction, but just those autoignition temperatures are just really low, and the temperatures and pressures in an aircraft engine are just so high. And I won't go through all these plots, but just demonstrating these points about, for example, if you have, this is now not an autoignition temperature, but it's saying, okay, if you are in a region where the mixture will autoignite, how long will it take? And so the y-axis is ignition time in microseconds, so this would be 1 millisecond. And you know, just to give you a ballpark, kind of a mixing time that we might use in a conventional system would be a couple milliseconds in order to give it enough mixing. But you can see that this would be, sorry, I keep looking at my screen and the mouse isn't there because there's two screens. But you know, this would be pure methane if you have 10% ethane, if you have 30% ethane. And so, you know, this starts to become a real issue as you start blending stuff into your gas. So what I want to do now is I'm going to do a little bit of a shift from the initial plan. And so I want to just talk a little about kind of where's the world going? You know, what are some of our prospects before I do a deep dive? Hope that's okay, because I feel like it might be useful context as you think about your future in combustion research. And, you know, really, there's what are combustion applications? Well, one big combustion application is natural fires. I'm not going to talk about natural fires, but that's really interesting stuff. As you know, look at the air quality. I have two daughters living in the state of Michigan right now, and you know, air quality from forest fires Canada. Another one is commercial space. That's really cool. You know, what's happening in commercial space is really interesting. Like everyone graduating from my lab now is going to work for commercial space companies in Seattle or California or Denver or Atlanta. Actually, we have a couple companies. Military applications, that's another one. But I'm primarily going to talk here about civilian type, either power or propulsion type applications. And really, the 900-pound gorilla in the kitchen is decarbonization, right? What does decarbonization mean, and what are those combustion challenges? And so, as I mentioned before, CO2 emissions are set by fuel, they're set by the cycle choice. That generally sets kind of the overall conditions for the combustor. So what that means is increasingly we're going to go to higher pressures because efficiency is really important. Because the higher efficiency, the lower the cost of the combustion-based solution. It means we're going to be looking at EGR type applications, and so you are all taking, I think you're taking Howard Herzog's where he's going to talk about carbon capture. You know, if you want to start driving up CO2 concentrations in exhausts, in the exhaust to make it easier or reduce costs for carbon capture. And so, you know, adding CO2 to reactants is as a simple example, is really interesting because CO2 is actually not an inert. I called it inert before, but it's not inert. CO2 interacts in all kinds of really interesting ways with combustion chemistry. You know, if you're trying to do pre-combustion carbon capture, which means you're pulling out the carbon before you combust it, that basically means you're burning hydrogen. So I think probably a good third of you are working on some hydrogen application. If you want to do post-combustion carbon capture, that means that you may be, well, I think I have a slide here. You know, if you want to do post-combustion carbon capture, you want a stream that you can that's preferably composed primarily of carbon dioxide and water, you know, you don't want all that nitrogen to have to deal with because, and so that means, you know, there's a lot of people looking at oxy-combustion systems. So I don't know how many of you are familiar with what's called the alum cycle. Okay, yeah, go take a look at it. It's kind of interesting. It's there's a lot of competing technologies, but the alum cycle is basically is trying to address the question of, let's suppose that you wanted to design a power plant that was optimized from the beginning for carbon capture, rather than trying to bolt the carbon capture unit onto the back. How might one do that? And really what it comes down to then is you want to burn oxy-fuel, so you don't want all that nitrogen floating around. And then you start, you know, integrating the air separation, the oxygen generation system with the power plant, with the CO2 stream. But what's really interesting about oxy-combustion is it's a little bit like rockets, except you're burning a lot more fuel. Just like we only burn fuel lean in air-breathing systems because you'd never waste fuel, right? You never burn fuel rich. Only rockets burn fuel rich. But you don't want to waste fuel. In the same way, if you're paying for the oxygen, you don't want to waste oxygen. So which means you're going to want to burn dead smack, dead nuts, phi equals 1, and so forth. And lots of really interesting combustion problems pop up when you start burning at phi equals 1, because phi equals 1 is actually kind of a crazy place to burn. Because if you think about it, if you're fuel rich, you got lots of extra air floating around, and the fuel molecules just have to find a friend. If you're fuel rich, the other way around. If you're phi equals 1, there's only one, there's 1 for 1, right? You don't have anybody extra. And so combustion chemistry gets a little bit crazy right around phi equals 1. Also, when we all learn combustion, we're used to thinking about equivalence ratio tendencies, which tend to be driven by temperature sensitivity. So as you change equivalence ratio, you change temperature. And so as we think about, oh, okay, lean flames are colder, stoichiometric flames are hotter. Well, now when you're burning with these oxy systems, you're actually going to be decoupling stoichiometry from temperature. And so it turns out a lot of things flip. So for example, if I were to tell you I'm going to burn oxy systems and I want to sweep phi, and the way you sweep phi at constant temperatures, you adjust a diluent ratio. And I wanted to plot what's the flame speed as a function of equivalence ratio for an O2 CO2 methane system, just as an example. I want to plot equivalence ratio, flame speed versus equivalence ratio. Okay, so we're all used to flame speed goes up, peaks near F equals 1, maybe a little rich, then it comes down. Anybody know what flame speed does in the system I just mentioned? So O2, CH4, CO2 system. I'm going to adjust stoichiometry by adjusting how much CO2 is in the system, and I'm going to fix temperature at, say, 1800 K. So if I adjust stoichiometry independent of temperature, it flips. So the lowest flame speed is at F equals 1, not the highest flame speed. And so anyway, what makes these oxy systems is that you really have to start differentiating the effects of stoichiometry and temperature separately because they start to decouple. And then other kinds of interesting things happen is that if you have to generate an exhaust, a combustion exhaust stream that is sequestrable or that you can put in a pipeline, you start changing your definition of pollutants. As an example here, I have a CO2 pipeline spec, all right, for EOR. EOR means enhanced oil recovery. This is where they actually built a carbon dioxide pipeline and they use it to pump CO2 to get more oil out of the ground. Similar issues, though, arise if you wanted to pump it underground. And you'll notice the spec. And okay, notice here CO, the Weyburn, it has a spec on CO. And the reason it has a spec on CO is because the carbon monoxide can react with the metals in the pipe. Notice there's also a spec on oxygen. Okay, so now actually oxygen, 10 ppm or 50 ppm, oxygen is kind of a, quote, pollutant if you want to be putting oxygen in a reservoir or in a pipe. Well, it's really hard to keep both CO and oxygen down at F equals 1. And just to illustrate this point, I have here a plot of equilibrium combustion. This is natural gas natural gas O2. This is phi, and I'm really zooming in on F equals 1. This is temperature. So, and the CO levels in parts per million are here. And so you can see that the CO levels are 100, I think that's 10, that's 1,000, 5,000, 10,000. You know, it really starts to take off as you go rich. And then O2 levels are the dashed lines. And so if you're running lean, obviously you're going to have excess O2, 5,000 ppm, 1,500, and then it starts to drop. So actually designing a combustion system that simultaneously, you know, is both low CO and both oxygen is non-trivial. So that's a real, you know, kind of an interesting. So bottom line is, keep your head up as you're doing basic combustion science. Who would have ever thought about this combustion problem? Like, how do I make a combustor that has almost no oxygen emissions, that emits 10 ppm or less O2 emissions? So, you know, pay attention to where technology is going, where policy is going, and that will suggest really interesting combustion problems that you could sit in your lab and just never ever think about. All right, so I think I'm going to go off script now. Hope is Mike here? Hope he's okay with that. Like I said, I'm going to actually be giving this talk. So what I just did was blasted through some of the R&D problems because actually I have this Gordon conference. I'll be giving a more complete discussion on that. And so what I'll do here is you're all going to be my guinea pigs. For this sort of 50,000-foot view is like, okay, world's changing. Like I said, decarbonization, sort of in the world of energy, the world of civil aviation transport, decarbonization's it's totally driving the policy and the funding landscape, and what's the role of combustion in it, in this rapidly evolving sector. And then if we think about combustion, what's driving combustion R&D in this new world? So I've kind of, so there will be a little bit of duplication here because I've made some references to it, but I want to tackle this in a more systematic way. And then what are the R&D needs in this new landscape? So let me just start by talking about, let's not even talk about R&D, but just to have combustion R&D, you sort of need, to get your society to fund it, unless you're independently wealthy, you need some macro driver. So what is the role of combustion R&D? So complicated question, right? And so I'm gonna again, like I said, you got to keep your head up in this new world. You got to think, what's driving these conversations? And these are boxes of things that are driving combustion conversations today. And I'll just briefly talk about each one of them. And I think probably the first one is maybe the one that we may be most comfortable with as engineers. And that's the question of, all right, let's assume that we want to get to net zero CO2. What's the least cost way to do that? What does that, let's just imagine a society where we're starting, we can't blow the world up and start from zero. We got to start from what we have today. So how do we get from point A to point B in a least cost way? So I'll spend some time talking about that. Yeah, actually, so let's go there first. So we can start by just saying, we'll just say, what's the world look like today? Oops, I need to make this macro. So you've all seen these Sankey diagrams. You know, what's on the left is what our fuel sources are, our energy sources are today, and you can see fossil gas is a really, really big one. You see crude oil, you see coal, you see uranium, you see wind, hydro, solar, tiny, small boxes. Over on the right-hand side, you see where that energy is being used. So the left is the sources, the right is the users of energy. So you see buildings. You know, buildings today are about 40% of electrical load, of overall energy load. You see industry, so this is agriculture and metals making and aluminum and things like that. And then on the bottom is the biggest CO2 emitter today in the United States is road transport, you know, cars and trucks, things like that. And then in the middle is, well, how do you go from where the energy is sourced to where it's consumed? So this is sort of, you can sort of think about this as the plumbing and wiring, right? So just like in your house, you've got, or your parents' house, whatever, you've got power lines outside, and you've got, you know, all the things that utilize that electric power inside, and so, you know, you've got all this wiring. And you got plumbing, right? And you've got source of water outside, and you've got these. So how's it all connected? So that what's in the middle shows the plumbing and wiring. And so one thing you can see that pops up in the middle is electricity. So electricity is what we call an energy carrier, right? It's not a source of energy, but it's a very useful way of transporting energy from the source to the user. But you also see that a lot of these things direct connect all the way from particularly if it's a fuel, from the left to the right. And so kind of a nice way to deconstruct, you know, that system is to say, okay, there's really three things going on there in that picture. We've got these energy sources on the left, which are largely non-dispatchable renewables. We got nuclear and we got fossil. And then on the right, we've got these users, which is basically industry and transportation and buildings. But don't forget in the middle, there's a lot going on in the middle. We've got all these ways of storing and carrying energy. And someone already referred to the electricity storage issue, but don't underestimate how important that is. Because if you think about how dependent we are all today on electricity, which is basically a just-in-time business. Just in time. So just think, you know, if I go dim those lights, there's actually a power plant the grid is adjusting. There is a power plant that's adjusting its power output. So the production, within a fraction of a second, the supply and the demand of electricity are balancing each other. And basically what happens is the grid frequency changes just a little bit, and that acts as a signal to the power producing sources. Think about what other major commodity our society is based on is just in time. Like, I don't know, bread. Bread comes from wheat. Imagine a world where your consumption of wheat was exactly balanced by the production of wheat. Or strawberries, or I don't know, any commodity, or I don't know, cotton for your shirt. It just, you know, we're used to a world in which, you know, things can get stored and it's made over here. But electricity, we don't really store it, although we're trying to really ramp that up. And it's really hard to move, right? You know, Ukraine makes a lot of grain, right? And it's shipped all over the world, or the US makes a lot of grain, or cotton's grown in, I don't know, Australia. So we kind of have these global ecosystems. So what's going on in the middle is really important, is how do we move this stuff around? Some things are easy to move around, like liquid fuels, big tankers. Some things are hard to move, like electricity. In fact, we don't move it. We don't move electricity back and forth between the US and Europe, for instance. Some things can be moved, but they're more difficult, like natural gas, because you have to cryogenically cool it. Tons of work going on right now, because if we'd say, well, hydrogen, we want a hydrogen economy, it's like, man, that stuff's hard to move, right? Either put it in a pipeline or you have to really make it cold, really cold, to make it a liquid. So anyway, what's going on in the middle is really important. And if you say, okay, what's going on in the world today? I mean, and this is the US. Electricity moves about 20% of the primary energy as a carrier. And the balance is actually fossil fuels. So fossil fuels acts as about 85% of our primary energy sources today in the US. And the reason that 85% is different from the 80 is just system efficiencies and things like that. But in terms of what the user's taking in, like your car is actually taking, the fuel is both the energy source but also the means of moving the energy to your device, about 80%. And so just a major point here is that as we think about the world we're heading into, it's kind of easy to think, oh, fuels are just energy sources. Well, actually, no, fuels are a lot more than energy sources. They provide 3 sources of value, right? They're an energy source, they're an energy carrier, they're an energy storage medium. All right? And if you think about where's the world going, the world we're heading into is already a little bit today, we differentiate between these two because we have 2 energy carriers. We have electricity and fuels. But increasingly, these 3 value propositions are going to get differentiated. They're going to be separately monetized. They're going to be in different technologies and systems are going to compete for them, for utilizing that. So just as an example, to illustrate what I mean, like I said, this is going to be a little bit more of an economic policy talk. Say, what's the value of fuel? You know, what's the value of fuel? I just said fuels do 3 things, right? They give you a source of energy. And just to illustrate the point that the value of a fuel is not just because it's an energy source. I have priced, this is EIA data, this is 5 different fuels, and I have put them all on the same price basis, which is price per unit of energy. All right? So if a fuel, which is the basis of our field of combustion, if the value it provides to society is the energy it provides, all these lines should be on top of each other. But they're not, right? And by the way, the x-axis is time, going back to 2000. And I have natural gas, I have ethane. So I can't remember who asked me the question about ethane, Minnesota, University of Minnesota. I'll talk about ethane here. Butane, propane, and crude oil. And you can actually see, well, from like 2000 to 2006, and in fact probably even before, the fuels were basically priced on an energy basis, right? They all track together. And then, does anybody know what happened in 2006? Somebody peels off. Natural gas peels off. Anybody know what happens there? Fracking. U.S. becomes, like, fracking takes off, and gas production in the U.S. just goes crazy. And before that, gas was pretty expensive. And all of a sudden, natural gas, and because it was expensive, it was used relatively limited, in a relatively limited fashion. In fact, some people don't know this, but during the crisis in the 70s, there was actually legislation making it illegal to use natural gas in this country for electric power production, and today it's the largest source of power production. But it takes off because all of a sudden there's relatively a limited set of users, but all of a sudden there's this big supply, economic supply demand, the price of natural gas starts dropping. Okay, so let's keep going. But the other fuels are basically tracking each other. So you can argue the value is the fuel itself. Okay, then right around, I don't know, what do you see, 2009, 2010, ethane peels off. Anybody know what's going on there? Well, and so just real quick, for those of you who are not aware of this, so like today, ethane is used, it can be burned, but it's also used for making plastics, like ethylene. So But what happened was a lot of the natural gas that was coming out of, like, let's say Pennsylvania is what we call wet gas. It has lots of ethane and propane in it. And so all of a sudden our ability, sort of our petrochem sector's ability to utilize that ethane to make plastics and chemicals, which is a higher value use, became saturated. They didn't need it anymore. So they said, well, we'll just inject it in the pipeline. And so then all of a sudden, you know, these fuels, and remember today, basically fuels are used for making chemicals, which is you get paid more in fuel as a power source. And so if it was now, and so for example, if you look at what's happening today, you see the price of ethane and natural gas are essentially tracking each other, which means it's whatever the value of that fuel is. Okay. All right, well, let's flash forward to where we are today. And basically, where we are today is you see things bouncing around a little bit, but notice there's basically two buckets. Right? We've got one bucket is ethane and natural gas, and the other bucket is propane, crude oil, and where is it? Butane. So this is what the market, and so notice on an energy basis, the market's saying, if you're butane, propane, or crude, I'm going to give you this much for a given amount of energy. If you're ethane and natural gas, I'm going to give you that much for energy. So again, if we think about those three value propositions, source of energy, carrier of energy, anybody have any idea what's going on here? There's physics here. Let's think about dew point. Well, all right, so standard temperature and pressure. What do you know about crude oil? It's a liquid. What's natural gas? It's a gas. And just basic physics 101, it's just a lot harder to move a gas, right? If you want to compress it, remember the compression loss. If you want to compress a liquid, it's pretty easy. It doesn't take much power to compress a liquid. If you want to compress a gas, it has this nasty tendency to heat up instead of just compressing. It's a lot less efficient. You have to chill it. And ethane is actually is basically a gas as well, whereas propane, pretty close to a liquid. So essentially what you have are, the market says, if you're a liquid, I'm going to give you this price for the unit of energy. If you're a gas, I'm going to give you this price for a unit of energy. So you can clearly see this point of this differentiation of value based upon whether you're a gas or a liquid that the market provides. So certainly it's a source of energy, and you can see what it's paying purely for the source of energy. The other thing that's happening here, actually, the reason you see this aggregation is, and this is somewhat unique to the US, is because natural gas prices in the US are so cheap, like $2 to $3 per million BTU. If you're in Korea or Japan, you're paying $20, 10 times as much. So there's this monster arbitrage between what's happening in the US and the rest of the world. And if you're just in the US, you don't necessarily appreciate how cheap energy is here. Whereas if it's a liquid fuels, what you pay at the pump for gasoline in the US is really not that different from anywhere else in the world. And why is that? It's because if you happen to be the person who owns that gas and you can get paid more for it in Europe, you're going to put it on a tanker and send it to Europe because it costs almost nothing to ship it there. It costs about $1 a barrel. Price of oil is $50 a barrel. It's 2%, right? Whereas natural gas, $2 to $3, it costs like $5 to ship it to Europe. And so basically what's happening is if it's a liquid fuel, you're going to pay what the rest of the world pays for energy. If it's a gaseous fuel, you're going to pay a US price. And so you get this big difference. But anyway, bringing me back to this point that I was going to say is we try to think about, wow, what's the role of fuels in the world that we're heading to, is just to remember fuels are not just energy sources, and you can clearly see the values there in terms of energy carriers and energy storage mediums. All right, so what would a net zero CO2 system look like? And so, all right, well, this is the million-dollar question, but there's actually a whole community. It's a really interesting community. Professor here at Princeton, Jesse Jenkins, is a real leader in this area, but basically doing what we call macro energy systems modeling, where you sort of put together a model of the overall energy system. And what makes these models tricky is you can't just sort of think about an average United States. You have to break this out by geography, by region. You can't just average over a year. The grid's got to work every second, right? We get impatient when our power goes out. So if on average it works, that doesn't matter. It needs to work at every instant. So you basically put these models together that are somewhat, it's a little bit like CFD, where you chunk the country up into blocks and then you break it out by time. And then you can wrap an optimizer around it and you say, okay, get me to net zero. What's the least cost way to get to net zero? And basically what ends up popping into is this new sector of energy carriers. So today, electricity is not a source of energy, but it's a carrier of energy. And so what these models want to do then is they want to say, not only do I want electricity, I also want fuels in the mix. But fuels that are not naturally produced from fossils, but that are manufactured via biological means or manufactured via some sort of catalytic process. And that could be a hydrogen, it could be a liquid fuel or something. That's one part. And then the other part, which I guess you're going to learn about this afternoon, is fossil fuels still in the mix, but with carbon capture. Could be pre-carbon capture, could be post-carbon capture. And then, all right, so what does that world look like? This is a picture of what that world might look like. So now I showed you the simple version, this is the more complicated version. But if you look on the left, you see, here's your sources of energy. And what's different? Well, you still have gas, but it's fossil gas, it's smaller. You still have crude oil, it's there, it's smaller. But solar gets really big. Remember, solar is non-dispatchable. Wind gets really big, also non-dispatchable. Nuclear is still there. Biomass gets much bigger. Then on the right, we have all these users of energy. But notice that all the plumbing and wiring just gets a whole lot squirrelier. You don't have a small number of big blocks. You got lots of little blocks going around. You still have electricity, but then you've got hydrogen, and in addition to hydrogen, you've got essentially these different liquid fuels. That's what this means. You've got ammonia, and so forth. And if you kind of break this thing out and say, okay, let's just think about big blocks. What does this thing look like? This is where the numbers are. Is that electricity as an energy carrier becomes much more important than it is today. So today we ultimately deliver about 20% of the power, the way energy is delivered to the users via electricity. It goes up to about 50%. And the reason for this, by the way, is transportation. Is that as we electrify transportation, that's why that number goes up. But note that number is not 100%. And so you just have to. I think there's a lot of misinformed people in the popular press that sort of envision this world where everything's going electric. Well, a lot more goes electric, but 50%. Where does the other 50% come from? It's all fuels, right? Green, you get this huge new sector that really doesn't exist today, which is renewable fuels. And this is where this fuel flexibility piece comes from, right? And again, this is ammonia, this is SAF, this is hydrogen, and frankly, our society, a really interesting macro question for our society is, what is the best chemical energy carrier today? We've got a century of experience using naturally produced fossil fuels, but if we could design or make our own fuel, what should it look like? And there's really kind of two questions around that, and this is where it gets thorny, is because there's cost of producing the fuel, and there is cost associated with the infrastructure that has to handle the fuel and the devices and machines that utilize the fuel. So what's the cheapest fuel to produce? Probably hydrogen. Simple, don't need any, what's the problem with hydrogen? If we were to blow society up and start from scratch, maybe it would be all hydrogen. What's the problem with that? Well, hydrogen is really hard to move. You got to get cryogenic. You get hydrogen embrittlement, right? So you can't use steel pipes. It'll make your pipes, it'll take if any of you are running hydrogen, you'll notice how your regulators and control valves, you have to replace them more often because hydrogen attacks the steel in them, et cetera. Or take like what's happening today in the aircraft industry is that there's this big controversy about what's the optimum path of, do we use drop-in or non-drop-in? How many of you know that phrase, drop-in or non-drop-in? Drop-in means, can I take a fuel and make it look and act just like fossil fuels do today? And so then but that way I don't have to change out any jet engines. I can use the same jet engines. They don't care about what fuel I can use the same logistics infrastructure, all that stuff. But then other people are like, but yeah, that fuel's more expensive to make. Why would we want to do that? Let's make a fuel that's cheaper. Well, then you move into the non-drop-in world, which says, okay, let's use a fuel that's the least expensive to produce, takes the least amount of energy, the overall, you can use, let's say, an electrolyzer powered by a solar farm to make that fuel, and you'll get the most fuel out of it. The problem with that is you need different jet engines, you need different transport infrastructure, all those the US has 2 million miles of pipelines, 2 million miles. Blow them all up. We don't need them in that world, right? We got to put new pipelines. I can take hydrogen, for instance. And so it's kind of this fuel cost versus turning over society trade-off that makes that question. It's a really interesting question, by the way. There's a ton of science around it because there's, what's this optimum fuel look like? But then just a ton of policy around it too. Is what does this what is this fuel-based energy carrier look like that's best? And then lastly, fossil fuels existing today, notice that's still 25%. That's a lot of fossil fuel. So it's not going, but with carbon capture, which is why you guys are going to have your talk by Dr. Herzog, who's an expert in carbon capture. I think I already said all this stuff. So I think major point here is that there's a lot of fuels showing up here. And not all these fuels will be converted into useful power via combustion. Some will use fuel cells, but a lot of them will, right? So there's going to be a lot of use for combustion. So, all right, so that kind of gives you a feel like, hey, if engineers were in charge of the world, and this was a centrally planned economy, this might be what our world looks like. But in reality, democracy is just so much more interesting and lively because politicians don't care what engineers think at the end of the day. And there's a ton of other things that get thrown into the mix, like geopolitics, like equity and energy justice, like reliability, jobs and existing infrastructure. I mean, a simple example is, if you think about it, we have take Europe, take the US, there is towns and people's jobs and people's livelihoods that are built around an existing system. And so let's just go to that question of what's the optimum energy carrier for the future. You might say, hey, in drop-in versus non-drop-in. As soon as you move away from drop-in to non-drop-in, guess what you're doing? You're disrupting that system. And the moment you disrupt that system, politics enter. Because you can say, I'm cool, I want to address climate change, but just don't make me lose my job and my house. The moment that happens, politics enters. And so if you say, Tim, what's your opinion? Drop-in is going to be the rule of the day, just because politics is just such a powerful force. And because drop-in means is that you can roughly, where people live today, where their jobs are, their that can remain. I'm going to jump over this. The other thing I would just say, what's also really important, I just want to, and there's a lot of interesting problems. In fact, Professor Michelson and I were chatting about this at breakfast, is the whole equity and energy justice. The idea that as we transition our energy systems, we want everyone to benefit. Our energy's a wonderful enabler of our quality of life, but also energy is our energy systems, whether it's our power plants or our automobiles, are also responsible for a lot of negative health impacts. One of the biggest drivers of negative health things, whether it's asthma or lung cancer, comes from combustion-derived pollutants. And so there's a lot of interest today in people saying, look, we don't want a society where the poorest 10% of people kind of get hosed and bear the burden of all this low-cost energy system. We want a society where everybody is flourishing and benefiting, which seems eminently reasonable. But what that means is that I showed you this picture, and this is the least cost way to get to net zero CO2, right? I didn't talk about air quality and pollutants. So there's intense interest today on the policy world of saying, you'll see a lot of environmental groups like, oh, that makes me really nervous. It makes me really nervous. what about NOx? What about soot? What about particulates? Can't we just bump this number up? We know that this doesn't do that as much. And so that's driving a lot of interest. So a simple example, this is NOx. If you heat up air, like we said, N2 and O2, you're going to get NO production, even from hydrogen. So if you look over the last 2 or 3 years, in fact, or particulates, even if you have a renewable hydrocarbon, a sustainable aviation fuel, if you're making particulates, it can still make particulates. So let's see, where do I have it? I'll just show you, just as an example. Well, actually, I'll come back to it. Okay, so anyway, so that kind of gives you kind of a view of where I think the world is probably heading. There's going to be a lot of combustion in this world, but increasingly the role of combustion is going to be utilizing a different set of fuels, where combustion is really around managing energy carriers around dispatchable power and things like that. Okay, well, with that background, what are the key R&D drivers in this landscape? And so I think really there's going to be 4. And so if those of you who are anticipating a future in combustion, this, at no charge at all, I'm giving you my cliff notes on where I think the future of combustion R&D is. And I think it's these 4 bullets. It's efficiency, it's operational flexibility, it's pollutant emissions, and it's fuel flexibility. And so in some sense this is obvious, but in some sense it's not. So let's start with efficiency. I'll talk 2 parts. So I think one is, as we talked about, the efficiency of a thermal power plant, Brayton cycle goes up with pressure ratio. And so think about all those interesting combustion problems that happen as you go to higher pressure ratio. And I think in particular, there's just really understanding the bifurcations about, okay, what can I understand by doing something at atmospheric pressure, but what do I really have to do at pressure to understand? And there's a lot of problems that simply the fundamental physics changes. A simple example is NOx. As I mentioned to you before, atmospheric pressure combustion, most applications, the NOx formed in the flame is the dominant mechanism. High pressure combustion, the dominant mechanism is post-flame. Fundamentally different scaling, fundamentally different sensitivities. So that's one example. There's lots of other ones. When we talk about flame stabilization, it turns out that flame stabilization, where flames can sit, is profoundly sensitive to pressure because flame thickness is really important. And flame thickness basically goes as 1 on P, 1 on pressure. So the difference in thickness of a 1-bar flame and a 20-bar flame is the 20-bar flame is 20 times thinner. So it can park itself in regions that a 1-bar flame could never think of existing. So just where the flame is, where it's stabilizing, which affects everything, is going to be so profoundly sensitive to temperature. I think a problem that this next generation of combustion researchers is going to have to tackle is sort of democratizing access to high-pressure facilities. It's simply, every university in this country can't have high-pressure combustion facilities. People will die. Things are going to explode. It takes a certain amount of environmental health and safety to just keep this thing safe. They're expensive. You got to have pressure vessels if you need windows. And so we need a smaller, the physics community has these big user facilities, right, where people write proposals to utilize a user facility. And I think we're going to have to figure this out as well. And then lastly, I'll talk about this a little bit more later, but just to motivate this, here's compressor discharge temperature. Oops, let me move. As a function of pressure ratio, and kind of obvious, but the temperature of the reactants is going up. And so what's happening is, if I think from Heinz Pitch class, what happens as you go up in reactant temperature? Well, basically the effective active, remember combustion is characterized by being a really high activation energy phenomenon. And so even the concepts like ignition and extinction, those are high activation energy words. Low activation energy reactions don't have ignition and extinction, But as you go up in preheat temperature, that famous combustion S-curve flattens out, and all of a sudden, effectively, you're going to lower activation energy, and you lose phenomenon like ignition and extinction, and it becomes more of a kind of a reactor type type physics. And one simple example is that deflagrative, premixed combustion is a reactive diffusive wave. It's this intricate coupling between reaction and diffusion. In a world where you're at higher reactant temperatures, where combustion is happening via autoignition alone without diffusion, just fundamentally different scalings, different sensitivities to turbulence and things like that. But I'll say a few more things about that later. Okay, that's part one on efficiency. And remember, efficiency is cost. So remember, combustion is going to be competing with lots of other technologies. It's going to be competing with fuel cells. Lower the cost, the more competitive it is. So I talked about higher pressure, but the other part around efficiency is higher turbine inlet temperature. So I showed you this slide earlier. I showed you this image on the right. And remember that for a combined cycle power plant, you want higher turbine inlet temperature. And the way, in those turbine inlet temperatures today are at the point where even perfect premixing, you make way too much NOx. So lean premixed combustion strategies, which is what the combustion community has focused on. You'll see hundreds and thousands of papers in the literature on this topic, motivated by low NOx. It's not sufficient alone. So how do you do NOx control at high temperatures? Well, probably the solution is shown right here, and this is axially staged combustion. I showed you this before, where you have most of the fuel coming on the front end, and let's just, if 1800 K is your magic number that you want to keep the flame temperature below, you keep the flame temperature below 1800 K, and then you dump the remaining fuel downstream, and it could be pure fuel, it could be a premixed mixture, or whatever. And the theoretical benefits of this are large, all right? We did a study on this a few years ago where we said, let's forget about real-world mixing rate effects, but let's just say if we took this thing and if we could mix instantaneously fast, what's the best possible NOx numbers you could get without violating any laws of physics? So, in other words, what's the foundational floor that we could push this technology to? And so this is a plot for a 25-bar combustion system, 20 millisecond residence time, temperature. This is NO ppm. This is DLN combustion, dry low NOx combustion systems. Looks like I got to fix my tab because that says 25 milliseconds and that says 20. So it must be 25 milliseconds. But you can see, and this is a log plot. This is NO. And you can see this exponentially rise. And just for your reference, EPA limits on NOx today are 30 ppm. But many cities, it's 9 ppm. Like Southern California, it's 3 ppm. So that kind of gives you a feeling for what the regulations are today. So 3 ppm is right here, 9 ppm is right there, 30 ppm is right there. And you can see DLN, perfectly optimized, will get you there until you get to about 1920, 1930 K turbine inlet temperature. But our friends who make turbines have now been able to develop technologies that get you above that temperature. So then what do you do? Then you can't meet compliance. So this is, but now if you say, all right, well, if we were to optimize one of these things, you get, the whole curve just drops by an order of magnitude and the temperature sensitivity drops. So this is what's fundamentally achievable. That delta between the orange and the blue, that's a career in research right there, is how do you get there, right? Because obviously, as you might expect, real systems, these systems are starting to be commercialized by the big manufacturers. But I can tell you they're not sitting anywhere close to that blue line. So how do you get there? And there's a ton of really interesting combustion problems buried in there. So for example, and I've got a couple problems here, is you got to premix that fuel in the air. So one of the challenges with this type of approach is that here you're premixing, here I was talking about the challenges with autoignition already. You've got fuel and you're dumping it into air of 800-900 Kelvin. That's hard. If you want to start now dumping fuel into combustion products, now you're at 1800 Kelvin, right? But it's got to be mixed. In order to get to that blue line, you've got to premix. So how do you dump fuel, premix it with an 1800 Kelvin crossflow? The good news is it's not just air. It's also there's oxygen, nitrogen, CO2, and water. But how do you do that? That's a really interesting challenge. And so premixing fuel and air at elevated temperatures is a big problem, is a big opportunity. And here I have a plot just to illustrate this. This is an OH. The orange is OH PLIF. The blue is PIV particles, and what we're doing is we're dumping fuel, that's here, this is what we'd call a reacting jet and crossflow, so we're dumping fuel into that hot combustion products there, okay? So hot combustion products, pure fuel. Anybody want to speculate on what the NOx production from this flame might be? Lousy, really bad. Why? I'm going to make a lot of NOx. This is not an optimized configuration. This is not the blue line. Pure fuel, oxidizer. What kind of flame is that? That's a non-premixed flame, right? That flame, where's the premix? If I'm dumping in fuel, there's no premixing happening there. So you've got a couple options to make this thing work. Either you've got to premix that fuel that's coming in some way, but you also have to push that flame downstream. That flame is anchored right at the nozzle outlet, and you want to say, don't anchor, please. Please move downstream so that you can get some premixing of fuel and air. And oh, by the way, and so in essence, if you want to push it down, what you want to do is you want to maybe crank up the velocity of that fuel. And so in essence, what the flame will do is it'll sit at it's going to auto-ignite, right? And so you can imagine if there's an auto-ignition time, let's say it's however many microseconds, and you've got so much velocity, that will give you the height at which the flame will lift. So you'd really like this flame to be lifted. Anybody have any thoughts on how that lifting height might scale with pressure? So if this flame is auto-ignition stabilized, so in other words, it's going to sit at a height where it auto-ignites. Auto-ignition times decrease with pressure. And kind of a rough rule of thumb I use, it's not perfect, is 1 on P. So going back to my prior question about high pressure is if you want to run a system at 1 bar and try to understand what it's going to do at 20 bar, well, at 1 bar, that flame could be really lifted because auto-ignition takes a long time. Whereas at 20 bar, that flame could come smack down. And so the difference, and because NOx is exponentially a function of temperature, you could be in 2 completely different worlds. One where the flame is lifted, it's mixing, super low NOx, the world looks awesome. Whereas at pressure, bam, down the flame comes, non-premixed flame, and it makes even more NOx than if you didn't do it at all. So, the other one I mentioned earlier is combustion under autoignitive conditions. In fact, most combustion textbooks haven't yet updated to talk about this. They talk about laminar flame speeds, but not auto-igniting combustion waves. But let's suppose you have a mixture that wants to auto-ignite. And let's suppose it takes 5 milliseconds for it to auto-ignite. Well, if the mixture is perfectly homogeneous, what will happen is you mix it, 5 milliseconds later, bang, the whole thing blows up uniformly in space and time. But that won't happen because in reality, there's going to be gradients. It'll be mixed better here, not mixed better there. So at one point, that auto-ignition time will be 5 milliseconds. Another point, it'll be 7. Another point, it'll be 3.2, et cetera. So what will happen is where combustion will occur first, 3.2 milliseconds, bang, it takes off here, and then 4 milliseconds there, and then 5 milliseconds here, and then 7. And so what you get is you actually get what looks like a combustion wave, but as autoignition is happening, as the clock is ticking, and basically the speed of that autoignition wave is going to be 1 over the gradient in ignition time. So spatial gradients, the grad tau ignition. I couldn't find there's the gradient, cool. So you see this, grad tau ignition. So gradients in ignition time control burning rates in this auto-igniting world. But the moment combustion happens in a spot, well, then a deflagration, a reactive diffusive wave starts to propagate away from that. How fast does that propagate? The speed of SL. So you've got this competition between deflagration and auto-ignition, and you basically get what's sometimes called a Sankaran number, which is SL divided by the auto-ignition wave speed, which is the same as SL times mag grad tau ignition. So here we have 2 really interesting basic combustion kinetic properties, right? Showing up in one equation, SL and not tau ignition, but grad tau ignition, with very different sensitivities. SL is really sensitive to high temperature chemistry, tau ignition sensitive to low temperature chemistry. There's a gradient in there, so there's turbulence mixing in and so forth. And this is a DNS, by the way, under auto-igniting conditions. And that top plot is heat release, the middle plot's temperature, the bottom is HO2 radical. But even just differentiating, like, if you're seeing reaction, is this reaction due to a deflagration? Is it due to autoignition? It's a really interesting problem diagnostically as well. So anyway, that's another really interesting problem. The last one I would just highlight is, in fact, but I better stop highlighting problems because I'm going to totally crush my schedule here. Okay, so those are just some really interesting problems that I see emerging in the future around efficiency. Let me just say a couple things about operational flexibility. I showed you this slide earlier. This is power output from a plant. And what happens is that I mentioned transient response, is that operational issues, let's suppose you test a combustor and you run it under quasi-steady state conditions and you map blowout, you match where combustion instabilities are, you map flashback. Those could be very different from under conditions under which it's dynamic. Let me give you a simple example. Suppose that you have a combustion system and you're running it at high power settings and it's really hot. The walls are really hot, but you have really high velocity so the flame doesn't flash back. And then you ramp down the power to another condition maybe where you decrease the velocity, but you also reduce the fuel air ratio. So under steady state conditions, the flame may not flash back. But under those dynamic conditions, what you could be doing is you could have really hot combustor walls because it'll take, you've got this thermal structure. So the thermal boundary conditions that this flame is interacting with in terms of where it's stabilizing, how it's flashing back, could be very different under quasi-steady conditions. So that can give you fundamentally different effects. And I'll give you an example of this, is that a major, I can't give you the details, but a major aircraft engine manufacturer had an issue a few years ago as they were certifying a new engine where they had a significant combustion instability when they were going through a transient. It was not an issue, let's say you're going from 60 to 50% power. I'm just going to make something up. 50% power, super stable. 60% power, super stable. But if I go, bam, from 50 to 60, monster combustion instability. And essentially it's due to this fact, is that the system is the combustion, you got these different time constants and the thing can really be out of equilibrium. So that's another interesting combustion problem, is just around the fact that thermal systems will increasingly be interacting with a lot of non-dispatchable resources, and the world is going to be a whole lot more dynamic. New combustion problems. Okay, pollutant emissions. I already talked about this, but as I said, there's growing scrutiny and pushback from environmental justice groups about combustion-based solutions, because they're basically saying, look, I don't want a world where there's air pollution, period, And so, rightly so, and this is a little snippet just so you can see the landmark. This is called Hydrogen Combustion and NOx, the new air pollution threat. What happens when hydrogen is combusted? Burning hydrogen does not produce carbon dioxide emissions. That's the good news. However, hydrogen combustion produces other air emissions. And the scientific fact, notice that word, the scientific fact, is the untold story in this aggressive industry plan, that one that could turn green hydrogen into ghastly hydrogen. The bad news is that hydrogen combustion can produce dangerously high levels of NOx. 2 European studies have found that burning hydrogen-enriched natural gas in an industrial setting can lead to NOx emissions up to 6 times that of methane. There are numerous other studies. Okay, so you can see the point. So it's a valid concern, but it's total garbage, total garbage. If you go look at the studies they're referencing, somebody basically ran a non-premixed flame, added hydrogen. Hydrogen burns hotter, stoichiometric hydrogen burns hotter than methane, right? You run non-premixed flame, you will make more NOx. Well, we wouldn't do that, right? We're going to run premixed because we're in a NOx-controlled world. And so, let me see if I have it here. I don't. So in fact, that little press release I showed you is several years old. I think there's a lot of data that's coming out where people are starting to report NOx numbers from premixed hydrogen systems, and the NOx numbers are actually lower than natural gas. In fact, we're just it just showed up in the preprint, is we just published a paper on premixed hydrogen natural gas blends and showed that NOx emissions comes down when you use hydrogen. It doesn't go up. But again, this just shows you why you got to keep your head up, right? Even as you're doing research, it's an interesting problem, and it's an interesting problem that comes out of this world we're moving into. And just, but obviously premixed hydrogen combustion is a challenge because of flashback. So that's why those first studies that they're quoting weren't running premix, is they just wanted to try something real quick and easy. And I think just generally speaking, NOx, high efficiency technologies with NOx, going back to what I talked about earlier, and then particulate matter. So I'm really glad that that as part of the summer school, Dr. Michelson talked to you about PM, particulate matter, because this is going to become more and more important. If you're watching the news, lots of interest today, for example, around natural gas-fired cook stoves and air quality in homes. Just go Google it. Very recent, last month. Lots of big studies, made all the major press stories about, hey, do we even want this stuff? Again, if it can get us to zero CO2, but we don't want our kids to have asthma, right? And so how do we deal with PM? So growing scrutiny around, not to say that this hasn't always been important, but I would just say it's increasingly important. I'm running way over time, but I think ammonia combustion is also really interesting. How do you do low NOx with ammonia? But I'm just going to jump past that. And then lastly, I'll just say fuel flexibility. We're going to spend a lot of time talking about fuel flexibility here because as all these operability issues that I talked about, blowout, combustion instabilities, flashback, autoignition, are very sensitive to fuel. And so balancing those with other combustion needs is going to be the issue. So just to kind of summarize my point around where's the world heading, Tim Lieuwen's prognostication is reminder that fuels provide not one value, but three values to the energy system. Those values are going to become increasingly differentiated, and combustion technologies will be entering this much broader milieu of potential sources of energy, users of energy, carriers of energy, and so forth. And sort of my take on the drivers that are going to control where combustion fits is really, again, it's around operational flexibility, emissions, efficiency, and fuel flex.